In this topic, you'll take a high-level look at the complexities behind developing bespoke machine learning models, but how also AI Platform, Google's managed machine learning service, makes it easier for machine learning developers, data scientists, and data engineers to take their machine learning projects from ideation to production and deployment. Earlier, you were introduced to the idea that leveraging machine learning can split into three areas. In this topic, you'll look at the more complex, but also the most adaptable option of those three. As a starting point, let's talk a little bit about TensorFlow. TensorFlow is an open-sourced, high-performance library for numerical computation, not just about machine learning, any numerical computation. In fact, people have used TensorFlow for all kinds of GPU computing. For example, you can use TensorFlow to solve partial differential equations. These are very useful in domains of like fluid dynamics. TensorFlow as a numeric programming library is appealing because you can write your own computation code in a high-level language like Python and have it be executed in a very, very fast way that matters at scale. The way TensorFlow works is that you create a directed acyclic graph, or a DAG, to represent your computation. Directed means it has a direction of flow. Acyclic means that it can't feed into itself, meaning that it's not a circle. And graph because it has those nodes and edges. In this schematic, those nodes represent mathematical operations, things like adding, subtracting, and multiplying, and also very more complex functions. Here, for example, softmax, matrix multiplication, and so on are mathematical operations that are part of this directed graph. Connecting the nodes are those edges, the lines, the input and the output of those mathematical operations. The edges represent arrays of data. Essentially, the result of computing the cross entropy is one of those three inputs to this bias add operation. And the output of the bias add operation is sent along to the matrix multiplication operation, or matmul. The other input to the matmul, you need two inputs to multiply a matrix together. The other input is the variable, or that's the weight. So where does the name TensorFlow come from? In math, a simple number like 3 or 5 is called a scalar. A vector is a one-dimensional array of numbers. In physics, a vector, I know everyone's trying to remember it right now, is something that has what? Magnitude and direction. But in computer science, we use a vector to mean one-dimensional or 1D arrays. A two-dimensional array is called a matrix. A three-dimensional array? Well, we just call it a 3D tensor. So a scalar, vector, matrix, 3D tensor, 4D tensor, and so on. A tensor is therefore an n-dimensional array of data. So your data in TensorFlow are tensors. They flow through the graph, hence TensorFlow. You can build a DAG in Python, store it in a saved model, and restore it in a C++ program for low latency predictions. You can use the same Python code and execute it both on CPUs and GPUs. This provides language and hardware portability. Like most software libraries, TensorFlow contains multiple abstraction layers. The lowest level of abstraction is a layer that is implemented to target the different hardware platforms, like running ML on your mobile device. In the latest version of TensorFlow, you also get the Accelerate Linear Algebra, or XLA framework, which is a faster compiler for all the math that underpins your ML models. Again, very low-level stuff here that you should probably know exists, but probably won't interface with directly. On top of that hardware, and moving up to more abstraction, is the execution engine for TensorFlow, written in C++ for highly efficient operations. You could write an entire TensorFlow function if you wanted to in C++ and register it as a TensorFlow operation. Generally, data scientists will use the APIs, which are a bit more abstract, and next on our list. Next are the familiar front-end SDKs, or software development kits, where you can use C++, Python, Go, Java, etc. to access your TensorFlow operations. I'll be honest with you though, a lot of my work in TensorFlow uses pre-built ML ingredients, provided through the Keras and Dataset APIs. Keras is a high-level neural networks API written in Python, and it can run on top of TensorFlow. Here's how friendly and abstract the Keras library is. You remember the deep neural network before that found the dog that's hiding in the laundry basket? If you're to use Keras, creating and adding those layers into that DNN would simply be model.add and how large you want the layer to be in units. There are some other concepts for image models like softmax and ReLU layers that you'll pick up when working with these different algorithms, but the code itself for building these layers is just like stacking block after block. Now let's talk about data size. If you have a small data set, like one that just fits in memory, pretty much any ML framework will work. R, Python, and so on, they have these statistical packages that are often 3 or 4 lines of code, and it'll just work. But these are in-memory data sets. Once your data sets get larger, these packages won't work. You'll need to split your data into batches and then train. However, you'll also need to distribute your training over many machines. Now, sometimes people think that they can take a shortcut in order to keep the training simple by getting a bigger and bigger single machine with lots of GPUs, but that's not the case. Scaling out is the answer, not scaling up. Another common shortcut that people take is to just sample their data so that it's small enough to let the ML use on the hardware that they happen to have. They're limiting the effectiveness of ML by not using all of the data for the machine learning model to learn from. Using all of that data and then devising a plan to collect 10 times that data that they currently have is often the difference between ML that doesn't work and ML that appears magical. Some of the other major improvements to ML happen when human insights come into the problem. In ML, you bring human insights, that's what your experts know about the use case or the data set, in the form of refinements to existing features or the addition of new features in a process that's often called feature engineering. You'll also need to pre-process your raw data, scale it, encode it, and these two things in a large data set also need to be distributed and then done in the cloud for scale. Now, that's just on the training side. Once you've completed and successfully trained your model, you want to deploy it for use in production. At that point, the performance characteristic changes. Instead of just thinking how long it takes to train on your training data set, you must also think about how it's going to support the number of prediction queries per second, or QPS, that you're going to need. That requires your solution being able to scale the prediction code as necessary to support the users who need to make those timely predictions. Now, the type of questions that you'll ask yourself here in the serving of your model are, what if the underlying model changes? You've retrained it. What if the parameters used in the model need to change? What if the number of inputs or the data changes? Do you really want to expose all this to your users? What if the client isn't in the language that you've used to train the model? Well, you can invoke the TensorFlow API from pretty much any programming language. And you can use cloud server resources to automatically scale out to as many of QPS or queries per second that you need for those predictions. But these are things that need to be managed, and that can be a challenge if you need to scale out that solution rapidly. Earlier we mentioned feature engineering and how to build those pipelines to pre-process your training data before training. This same pre-processing must also happen at prediction time too. But beyond just cleaning up the data, there's a variety of ways that your trained model could be a bit different than your prediction one. Using a standard like AI platform helps minimize these issues. While it's rarely talked about, your prediction inputs will often be systematically different than the ones that you use to train your model with, in subtle and hard to detect ways. Maybe the average of some column has shifted, or the variance has grown over time. This is a phenomenon that we call training serving skew, and detecting it requires continual data collection and re-examination. AI Platform simplifies this for you, ensuring that the trained model is what you actually run. In other words, it helps you handle that training serving skew. AI Platform will keep track of all those pre-processing and feature engineering steps for you, as well as allow you to version your model over time. In training, AI platform will help you distribute that pre-processing and train your model multiple times iteratively, and then help you deploy your trained model to the cloud for predictions. Now, when we talk about predictions, the ML model is accessible through something like a simple REST API, and it includes all the pre-processing and feature transformation that you did, so that the client code can simply supply the raw input variables and get back a prediction. AI platform can also distribute the model as needed to supply a high number of queries per second. Those are the people that want to make predictions with your trained model. With ML, you need both high quality execution at training and prediction time. If you've got a great model, but it's super slow for those timely predictions, no one's going to use it. While the computation of a TensorFlow model once is relatively cheap, the point of an ML model is to make those predictions for lots of incoming requests. Let's look at a diagram that provides a high-level overview of the stages in the ML workflow. The blue filled boxes will indicate where AI platform provides managed services and APIs for you to use. You must have access to a large data set of training data that includes the attribute, that's the label, the correct answer for machine learning. And that's what you want to be able to infer or predict for the future based on all the other data that you have. Your other inputs are called features. For example, assume that you want your model to predict the sale price of a house. Begin with a large data set describing the characteristics of houses in a given area, including things like the sale price of each house, when it was sold on, so on and so forth. After you've sourced your data, you've got to analyze it and understanding the data and pre-process it to get it ready for machine learning. In this pre-processing step, you transform valid, clean data into the format that best suits the needs of your model. TensorFlow already has a lot of pre-processing libraries that you can use automatically with AI platform. In addition, consider other GCP services that we talked about, like BigQuery, Cloud Data Proc, Cloud Data Flow, Cloud Data Fusion, and Cloud Data Prep to help you with those transformations. A lot of the work in machine learning is just getting that clean data ready for machine learning. Then you can develop your model using established ML techniques or by defining new operations and approaches. You can start learning how to create your model by working through the documentation provided by TensorFlow, Scikit-learn, and XGBoost. AI platform provides the services that you need to train and then evaluate your model all in the cloud. When training your model, you feed it that data or those input features for which you already know the value of that target data attribute, the historical right answer. Again, that's called the label. You then run the model to predict those target values for your training data so that your model can adjust its settings to better fit itself to the data and predict the target value more accurately. This is the whole learning part of machine learning. Similarly, when evaluating your trained model, you feed it data that includes the target values. You compare the results of your model's predictions to the actual values for the evaluated data, and then you use statistical techniques appropriate to your model to gauge its success. That's how well it learned. You can then tune the model by changing the operations or the settings that you use to control for training purposes. These are called hyperparameters, such as the number of training steps to run in training. This technique of adjusting those model knobs is called hyperparameter tuning. AI platform provides tools to upload your trained ML model to the cloud, so then you can send prediction requests to the model. In order to deploy your trained model on AI platform, you first must save your model using the tools provided by your machine learning framework. This involves serializing the information that represents your trained model into a file that you can then simply deploy for prediction in the cloud. On GCP, you would upload the saved model to a Google Cloud Storage bucket, and then create a model resource on AI platform, and you just specify that cloud storage path to where your saved model is located. AI platform provides the services you need to request predictions from your model in the cloud. There are two ways to get predictions from trained models: online prediction, sometimes called HTTP prediction, and batch prediction. In both cases, you pass input data to your cloud-hosted machine learning model, and you get those inferences for each data instance. and you can monitor the predictions on an ongoing basis. AI Platform provides APIs to examine all your running jobs. In addition, various GCP tools support the operation of your deployed model, such as the entire suite of tools within Stackdriver. AI Platform provides various interfaces for managing your model and model versions, including a REST API, the G Cloud AI Platform command line tool, and through the GCP console.